So when you ingest lipids, or triglycerides at least, they're too big for them to get through your intestinal wall, from your small intestine into the mucosa of your duodenum. And so your body breaks them down. First it emulsifies them, and then it breaks them down even further using doing triacylglycerol hydrolysis. And after that step, you end up with these three pieces. You have 2 fatty acids and 1 monoacyl glycerol, because you have that one acyl group on this glycerol backbone, so monoacyl glycerol. So you have these 3 pieces now, and those are small enough to travel through your intestinal lining into your mucosa. But once they're there, your body puts them all back together. So you end up kind of where you started, with the original triacylglycerol, or triglyceride. The only difference is where it is. Instead of being inside of your digestive tract, it is now in your mucosa and can be transported to other places in your body. So in this video, we're going to talk about how your body puts these pieces back together, how you resynthesize the triacylglycerol. So this is triacylglycerol resynthesis. Now, the first thing to note is that these fatty acids are indeed acids. So they're fatty because you have this long nonpolar part on the right, and fats and lipids in general are defined as biological molecules that are soluble in nonpolar solvents. So this is nonpolar, so by definition it's fatty. And then the other part is this carboxylic acid head that you have. And it is an acid because the bond here, acids can give away H pluses. So imagine that this H plus, so just the hydrogen ion, not the electrons attached to it, that pops off the molecule as this molecule jostles around. These electrons then would snap back onto the oxygen to form a lone pair. That oxygen now has 3 lone pairs and a full negative charge. And normally that would be really unstable and it would just steal the hydrogen back. But because these lone pairs, the lone pair that's formed is allylic to this pi bond, it's 1 atom away from an atom in a double bond, the charge can spread out through resonance, and when charge spreads out, it becomes more stable. So this can exist in a p orbital that's parallel with the p orbitals forming the pi bond here. And because of that, the electron can spread out over all 3 of those atoms, and that stabilizes or dilutes and stabilizes the negative charge. And so this is stable, and that's what makes it acidic, because it can give away these H pluses. And so that is indeed what happens to this fatty acid when it's in your body solution. So it's actually wiggling around looking like this. And it's at that point, as this stronger nucleophile, that it can start to react to be put back together with our other pieces here. So this molecule then wiggles its way over toward, at the same time that that's happening, losing its hydrogen, an ATP molecule, so this adenosine triphosphate molecule. And notice this has a couple parts, right? It has the adenosine part, and then so that's this part, and then it has the triphosphates. There's 1 phosphate, 2 phosphates, 3 phosphates, triphosphate. So that's the ATP. And ultimately, the adenosine part, the green part, is kind of an archaeological thing. These biological compounds are so big because they evolved over time. So they tell you a little bit about the history of life. And the main function of the adenosine part is, first of all, these pieces are very available. They're used in a bunch of other biological molecules, including DNA. So they're really available to make stuff with. And then this usually accounts for things like solubility and making sure that the functional part of the molecule can reach the places it needs to, the right enzyme sites. So the really workhorse part of the molecule is the triphosphate part. And the reason for that is because each of these phosphates is a great leaving group. These phosphates are great leaving groups for the same reason that the carboxylic acid of the fatty acid is acidic. Because if you have one phosphate and it gains, let's say this leaves, and that oxygen gets a negative charge, that negative charge is allylic to this double bond. So the negative charge can exist in a p orbital that's parallel with the p orbitals forming the pi bond, so that negative charge can spread out and dilute over those atoms. So the phosphates are really good leaving groups, and that's what's going to happen here. The phosphates are going to get attacked. This fatty acid chain, the oxygen on it, is a nucleophile. And so that nucleophile is going to want to attack one of the phosphoruses because the phosphoruses are bonded to lots of oxygens. So it's really losing its electron density and it's becoming really slightly positive. The only problem is that there's a bunch of negative charge around there already. And so if this fatty acid tries to swoop in there, it's going to get repelled by that negative charge. So to allow this nucleophile to attack the electrophilic phosphorus, slightly positive phosphorus, these negative charges need to be neutralized a little bit, and a magnesium ion comes in to do that. So a magnesium ion swoops in. This is a free magnesium ion in solution, and the positive charge there sort of neutralizes and takes care of a couple of these negative charges near the phosphorus that's going to get attacked. So once you have that, your fatty acid can swoop in, and really we're going to do an SN2 reaction. So this nucleophile can attack the phosphorus electrophile, and at the same time, it will expel a leaving group. Now the leaving group, I'll put in green here, the leaving group is going to be this group right here. So it's an SN2 reaction. We have our nucleophile over here, and our leaving group in green. So these electrons will go onto that oxygen, which we said was going to be really stable because it can be stabilized through that resonance, because that lone pair is going to be allylic. And we're going to end up with sort of two pieces after this. So let me copy these. Okay, first piece is we're going to have what's called inorganic diphosphate. The electrons in that bond are going to go onto that oxygen. So these two phosphorus groups now, these two phosphate groups are kicked off. They're their leaving group, and this is a diphosphate, right? Because you have one phosphate, two phosphates, so it's a diphosphate, and it is inorganic because it's not attached to any carbons. So that's sometimes symbolized as PP because you have two phosphates with a little I because it's inorganic. So this whole thing is that PPI, that diphosphate, inorganic diphosphate. At the same time, let me move this double bond over. That's still going to be there, of course. But at the same time, this fatty acid will now be connected there. So the lone pair, what was a lone pair, will now be attached to that phosphorus. And let me actually move that over. So we'll have that and there. Okay. And at this point, this magnesium, can go away, can diffuse. There's not enough charge there to make it stick around. Probably it goes off with the inorganic diphosphate. Okay, so this is what we're left with. This is no longer adenosine triphosphate because the diphosphate has left and a fatty acid has come in. This is something called an acyl adenosyl phosphate. So we'll anchor ourselves by the phosphate, right? On one side of the phosphate, we've got that acyl group, and on the other side of the phosphate, we have the adenosine group that we had before, so that adenosine group. So you've got an acyl adenosyl phosphate there. Okay, so what we've done was an SN2 reaction where a fatty acid chain replaced an inorganic diphosphate. So now we're going to do a nucleophilic acyl substitution, this classic sort of biochemistry reaction, nucleophilic acyl substitution. So we're going to take this acyl adenosyl phosphate, and it is going to react with another really important molecule called coenzyme A. Coenzyme A. Now, again, like with a lot of these biological molecules, there's a part of the molecule that's sort of an artifact of ancient life that serves purposes of solubility and making sure the molecule fits into the right enzymes, and then there's the active part of the molecule. So the artifact part of the molecule is this whole thing here. Notice how similar that is to the adenosine in ATP. Right? You just have this phosphate group down there, which is a little weird, and you only have 2 phosphates over here, but that's that's interesting there. The rest of the molecule is not even the active part. A lot of this is not going to interact now. I'll put this in blue. This whole thing is a molecule called phosphopantothane. It's not necessarily important for our purposes here. What's really going to react is the sulfur at the end here. Sulfur is a great nucleophile. It's pretty electronegative, so it's got a slightly negative charge, but the crucial thing is it's really big. It's immediately below oxygen on the periodic table. As you go down in a column, atoms get bigger. And when they get bigger, that means that if there's a positive charge nearby, there's a lot of front row seating. All the electrons can have plenty of room to get close to it. And so you build up a huge negative charge on one side that makes them very prone to attacking positive charges. In other words, it makes them very nucleophilic. And if you had a small atom, you wouldn't be able to do that. If you had a small atom, if all of, like oxygen is, if all the electrons try to line up in one place, they crowd together and repel each other until they spread out again. So sulfur is big, and that makes it a better nucleophile because it's able to create these poles, these slightly positive and negative ends in a single atom. So it's called very polarizable. Okay. So sulfur is going to be our nucleophile in this next nucleophilic acyl substitution reaction. That's going to happen on this carbon here. But first, we're going to make it an even stronger nucleophile. Although it is a strong nucleophile already, we're going to make an even stronger one. We're going to use this enzyme, acyl-CoA synthetase. And notice there are two types of enzymes here that have very similar names. One is called a synthase, and one is called a synthetase. Both of these make things, they put things together, syn. A synthase puts it together without using ATP, and a synthetase puts things together that require ATP. So you can see we've already used ATP. This reaction requires ATP. This enzyme, the action of this enzyme requires for ATP to be used. So it is a synthetase, not a synthase. Notice also the ASE ending means you always have an enzyme. Okay, so right now this acyl-CoA synthetase is going to function just as a base. And this can be anything that has a lone pair, anything that has a negative charge. In it, it's going to steal the hydrogen off of the sulfur, and the electrons will move onto the sulfur. So ultimately what we're doing here is a proton transfer. We're moving an H+ from coenzyme A to the enzyme, acyl-CoA synthetase. And that's going to make this a stronger nucleophile. So let me just do that here. Now this sulfur has 3 lone pairs. It had 2 before. Now it's going to have 3. And this hydrogen is going to move over to this base, which will now have a plus charge. And the sulfur has a negative charge. So it's a great nucleophile now. Okay, so now that this sulfur of coenzyme A is a strong nucleophile, it can attack the carbon of the fatty acid. So this can swoop in, attack that carbonyl carbon, and that carbon is slightly positive, right? Because it's bonded to the 2 electronegative oxygens. So it'll swoop in, attack that carbon. The weakest bond, the pi bond, will break. The electrons will go up onto the carbon there. And what we're going to have is a tetrahedral intermediate, right? And that's what you get every time you do these nucleophilic acyl substitutions. So we're going to have this tetrahedral intermediate where this lone pair is going to become a bond. I'll move this over. We're going to have only one bond to that oxygen. I'm just going to draw this in a different direction to make room, but only one bond to that oxygen, 3 lone pairs on it, full negative charge. And then the sulfur, with its 2 electrons, that will be able to swoop in. And let me actually get this a little bit closer, if I can. All right, so we'll leave it how it is. This will just be a slightly awkwardly long bond, but there it is. There. So that is our new tetrahedral intermediate, right? This carbon is now sp3 hybridized and tetrahedral. Okay. Well, our base is still, the base of our acyl-CoA synthetase still has that positive charge, and what it can do is it can donate that to what is going to become our leaving group. So our leaving group is this whole thing here. And that's ultimately being replaced by what was our nucleophile, which is the coenzyme A, this whole thing here. So we need to make this a slightly better leaving group. And really, right now, it's not the worst leaving group, because if it did leave, this would have a negative charge, it's true, but it would be allelic to this pi bond there. So it probably could pop off even just like that. But if you want, you could make it an even better leaving group by doing a proton transfer. I guess for simplicity's sake, we'll omit that proton transfer, because it is a good leaving group already. And this can swoop back down and kick that leaving group off. So now, we will have this bond breaking and becoming a lone pair on this oxygen. And so this group is going to leave. Let me just make sure it takes that with it. Okay, this whole group is going to leave, and this group is actually AMP, adenosine monophosphate. That's AMP. AMP. Because you have the adenosine, that's this group right here that has been reappearing so often, and then you only have one phosphate on it. So monophosphate. So we have this AMP. So we've used ATP, it's become AMP, and our molecule of interest now has a double bond. So this lone pair is going to move back. I'll have a double bond here. I know this looks really awkward, but it's okay. So right now, what we have is ultimately, if you notice, this group, this group right here, is basically our fatty acid. But we've replaced the OH that was there in the fatty acid with this other group. And that other group, this whole thing, this big coenzyme A, is ultimately just a gigantic leaving group. So what we've done is we've replaced a bad leaving group, the OH of the fatty acid, with a good leaving group, coenzyme A. And so now we have made this molecule. This molecule here is called fatty acyl-CoA. So we have attached the coenzyme A, that's the green thing, to our fatty acid. Okay, well, we did that for one of the two fatty acids. So we did that for this one. That same process, so now this is not going to be there anymore. That's going to be this fatty acyl-CoA. That same process is going to repeat for the other fatty acid. So let's quickly repeat that process for that other fatty acid. So this hydrogen is acidic because as this molecule jostles around in solution, something else can stick to the hydrogen, rip it off as an H+. Oops. The electrons here will snap back onto that oxygen. So it had 2 lone pairs before, now it has 3. It's a full negative charge. That's stabilized through resonance over all 3 of these atoms. So that negative charge is diluted in space and stabilized. So this is how our fatty acid appears as it wiggles through our solution. Now this, at the same time that that's losing that hydrogen, ATP is going to coordinate with this magnesium. The phosphorus, these phosphoruses are an amazing electrophile. They're bonded to a lot of oxygen, stealing their electron density, so they're slightly positive, but the negative charges around these would repel an incoming nucleophile. So this magnesium coordinates with those and sort of neutralizes these negative charges near where the nucleophile is going to attack ATP. Fatty acid swoops in. Here I'm going to erase this positive charge that's on phosphorus. It's still there, but the oxygen nucleophile of the fatty acid attacks the phosphorus. Our leaving group, remember, is the inorganic diphosphate. So that gets kicked off. Oops, these electrons get kicked off onto that leaving group. And so, ultimately, this bond becomes a lone pair on this oxygen, which now has 3 lone pairs, and therefore a negative charge. And what we have is inorganic diphosphate. Inorganic diphosphate. And I'll erase these coordination lines here. Magnesium most likely goes with that to accompany the negative charges. So this inorganic diphosphate, which is symbolized as PPI, right? 2 phosphates, 1, 2, and it's inorganic I because it's not bonded to carbon at all. So that diphosphate leaves, and this, I'm going to move this carbonyl, the double bond to the oxygen, over a little bit so that there's room for this incoming nucleophile to come in. What was a lone pair becomes a bond between, oops, wrong place, becomes a bond between the oxygen and the phosphorus. I might have had that drawn incorrectly above. Let me just make sure. So that oxygen should have been attacking that phosphorus. Hopefully I had it that way. But it's the phosphorus that has the slightly positive charge. Okay, so this is no longer adenosine triphosphate. It is now an acyl adenosyl phosphate, because you have the acyl group and the adenosine group attached to the phosphate. And now this acyl adenosyl phosphate can react with our next molecule, which is coenzyme A. Now it's really just the sulfur of coenzyme A that's going to react with this. And to activate that sulfur as a stronger nucleophile, the enzyme acyl-CoA synthetase acts as a base, steals the hydrogen, the electrons go onto the sulfur, so it's a proton transfer. So that hydrogen is going to move off of the sulfur onto the base. That base will now have positive charge somewhere, and then the electrons on the sulfur will become a third lone pair. There were already two, there's going to be a third one, and the sulfur has a negative charge now. So it's a great nucleophile. So now we can take this coenzyme A molecule, and it is going to do a nucleophilic acyl substitution reaction with this fatty acid. So ultimately, this group here, which is AMP, is going to be our leaving group, and the coenzyme A is going to be our nucleophile, and it's going to be a nucleophilic acyl substitution reaction. So in those reactions, the first step is nucleophile attacks the carbonyl carbon, the weakest bond, the pi bond breaks, the electrons go up onto the oxygen. So I'm just going to draw that in here. I'm actually going to move this oxygen over a little bit just to make some room. So that oxygen now has 3 lone pairs and a full negative charge. And the sulfur is going to use one of those lone pairs to attach itself to that carbon. Okay, so now we have our tetrahedral intermediate. This carbon here is sp3 hybridized and tetrahedral. Well, this oxygen is very unstable. It's got a full negative charge. This carbon here is slightly positive because it's bonded to a lot of electronegative elements. And so it wants to bond to it. So it swoops back down. When it does that, it kicks off the best leaving group, and that is the AMP molecule, because a negative charge on this oxygen will be allylic to this pi bond, and so it'll be able to spread out through resonance. So this lone pair will become a pi bond. This bond will become a lone pair. That will now have a full negative charge on it, that oxygen. And what we're left with there is AMP. Oops. So this is no longer acyl adenosyl phosphate. This is now adenosine monophosphate. Or AMP. There's your adenosine, there's your 1 monophosphate. And what we have here again is a second fatty acyl-CoA. Right, we have our fatty group here, what was our fatty acid, and then we have the thing that replaced it that ultimately is going to act as a good leaving group, our CoA there. So we have a fatty acyl CoA. So what we've accomplished now, after these 2 steps, is now we started with these pieces, right? Our goal is to resynthesize the triglyceride. That's what's happening now that these smaller pieces have been transported from your intestine into your duodenal mucosa, in the mucosa of your duodenum. And what we've accomplished so far is that each of these fatty acids has been replaced by this fatty acyl-CoA. That's what we've accomplished so far. So now, in the next step, we're going to see how these can recombine. So these pieces are going to be reattached through nucleophilic acyl substitutions. In this case, the nucleophile is ultimately going to be the OHs. The nucleophiles are going to be the OHs on the monoacyl glycerol. So this glycerol already has 1 acyl group there. It never left. It's a small enough piece to travel through your into your intestinal mucosa. But now, once it's on the other side, this is going to act as a nucleophile and do a nucleophilic acyl substitution reaction. And I guess I should put those in red. Right, this is going to be a nucleophile. And then the leaving group of this nucleophilic acyl substitution is going to be this big coenzyme A molecule. And so you can see that will reattach this fatty acid here, this purple fatty acid, onto the glycerol backbone. So let's walk through that for each of these guys. Take these here. Now, this is going to use a couple enzymes. The enzymes have long names, but one thing to remember about these long names is when names are long in science, it's because they're not really names, they're really descriptions. They're like complete descriptions of something. And so as a name, it's very long, but if you think of it as a description, it's pretty complete. So the enzyme we're going to use is monoacylglycerol acyl transferase. Why? Because we are putting one acyl group, so we're taking a monoacylglycerol. So here's our glycerol with our monoacyl group. And we're putting another acyl group onto it. This other acyl group, we're transferring it onto it. So monoacylglycerol acyl transferase, the abbreviation for that is MGAT. M for mono, G for the glycerol, A for acyl, and T for transferase. So it's an enzyme. Now, in this scheme, what will happen is the base is going to steal the H off of cysteine first, inside the base. This base is going to steal this hydrogen off of cysteine, and these electrons are going to snap back onto the sulfur. So I'm going to move this down for now, get this a little out of our way. We'll be dealing with that in just 1 second. But for now, let's take this, move this right side up. Okay, so for now, when you do this proton transfer reaction, this lone pair becomes a bond. This hydrogen moves on to it. The other lone pair, or the electrons in that bond become a new lone pair, and the sulfur now has a full negative charge. So it's an extremely strong nucleophile now. And now that you have that strong nucleophile, you can do your nucleophilic acyl substitution. The electrophile it's going to attack is the carbonyl carbon of the fatty acid. So this will attack, swoop in, attack this carbonyl carbon. The weakest bond breaks, that's the pi bond. The electrons go up onto that oxygen. So those two now become a lone pair on the oxygen, which has a full negative charge, and the sulfur is going to, of the MGAT is going to be bonded. Oops. That sulfur is going to be bonded to that what was the carbonyl carbon. Okay, so we're doing a nucleophilic acyl substitution. This is our tetrahedral intermediate. Right, this carbon right here is sp3 hybridized and tetrahedral. So this oxygen is very unstable, and it's going to want to swoop down and kick off the best leaving group. Right now, both of these are about equal leaving groups. So one thing that the enzyme can do is it can do a proton transfer onto this sulfur. So the sulfur the lone pairs there can steal this hydrogen. The electrons snap back onto the base. And what was a lone pair ends up being a bond to that hydrogen. So now the sulfur has a positive charge and it's a really good leaving group. Full positive charge there. So then this negative oxygen, which is allured by that carbon beneath it, can swoop back down to recreate the pi bond and kick this leaving group off. The coenzyme A leaving group off. So this bond becomes a lone pair on the sulfur, which takes that positive charge away. And that's going to move this CoA enzyme that CoA molecule. So that gets moved away. And this oxygen no longer has a negative charge because one of the lone pairs swept down and became another pi bond. So these molecules are sort of playing hot potato with these acyl groups, these sort of fatty acid chains. They're not carboxylic acids right now, but the carbonyl and the long chain is getting passed from one thing to another in these sort of cascades. So now that we have this molecule here, this acyl enzyme, now that we have that, we're ready to react it with our monoacyl glycerol, right? One acyl group on glycerol, monoacyl glycerol. And it's going to be another nucleophilic acyl substitution just like the one before. Oops. So we can take this, and the first thing we need to do is make our nucleophile a better nucleophile. So let me just do this. Okay, oops. Line it up a little better. So we can make our nucleophile a better nucleophile. Now remember, our nucleophile is going to be this oxygen here. It only has a slightly negative charge now. We can give it a full negative charge by doing a proton transfer. The base can swoop in, steal that hydrogen. The electrons would snap back onto the oxygen. So that'll snap onto that oxygen. That oxygen had 2 lone pairs. Now it's going to have 3. That will give it a full negative charge and making it a really strong nucleophile. The base, the lone pairs on it, that's going to become a bond, and the hydrogen will be at the other end of that bond. Okay, now that we have this strong nucleophile, the nucleophile can attack our electrophilic carbonyl carbon. Right, this carbon right here is slightly positive, so it can swoop in, attack that. The weakest bond breaks, that's the pi bond. It's going to swoop up there, and actually let me do that on the other side. So this pi bond will become a 3rd lone pair on that oxygen. That gives us our negatively charged oxygen. And I'm going to draw this bond a little long, but that lone pair is going to be this bond here. That's really long, right? And we have a tetrahedral intermediate now. This carbon here is tetrahedral. And this oxygen is unstable. It wants to snap back down and reattach. The lone pairs want to snap back down and reattach to the carbon there. But right now, we don't really have a good leaving group, so to make this sulfur a better leaving group, we can do a proton transfer. So the sulfur can steal the hydrogen there, the electrons snap back onto the base. Notice how the base ends up exactly how it started. That's why it's a catalyst. An enzyme is a biological catalyst. It makes a reaction happen without changing itself. The sulfur is now bonded to this hydrogen, and because the sulfur has 3 bonds, it has a full positive charge. It's in group 6A, just like oxygen. So when it has 3 bonds and 1 lone pair, it has a positive 1 formal charge. And now we have a great leaving group, because if this leaves, it'll become neutral. It'll become more stable than it is right now. So these lone pairs can swoop back down, kick our leaving group off. So our leaving group will go away. That'll take care of that negative charge. Our MGAT, monoacyl glycerol transferase, has served its purpose. And oops, let me just connect that there. And this lone pair is shared now, so it's not just going to give its charge to that oxygen, and it's going to be a pi bond. Oops, let me actually. It'll be a pi bond between those 2 atoms. And so notice, I know this is drawn in a way that's a little weird, but notice that this here, what we've accomplished so far, is we have attached the acyl group back onto the glycerol backbone. So really, we just need to go through that process one last time for this other OH, and we'll have the triglyceride back. So actually I can redraw this just so it looks a little more intuitive. Let me move this oxygen over just a little bit. There we go. And that bond there can go and attach to this oxygen here. So you get a somewhat of a better sense about how we've attached that group there. So the last thing we need to do, so this is now where we were. The last thing we need to do is to attach our last acyl group onto this chain, right? This is now not a triglyceride, but a diglyceride. You only have 2 fatty acids on this glycerol backbone. So we need to take this and attach our last carbon chain on it, and we're really going to do it in the same way. It's just instead of starting with the monoacylglycerol, we're going to start with this diacyl. So, because we're starting with a diacylglycerol, right, you have 2 acyl groups on your glycerol backbone. Because you're starting with a diacylglycerol, the enzyme is going to be different. It has to accommodate this different shape in its active site. So it's going to be called diacylglycerol acyl transferase, because we're transferring or putting another acyl group on here. So it's diacylglycerol acyl transferase, or DGAT, and it's just going to be a catalyst, biological catalyst, an enzyme that's making this reaction go. And it has a cysteine on it, just like MGAT did. Now at first, what we need to do is to attach, we're not quite ready for this diacylglycerol just yet. We have to take our fatty CoA and attach it to our enzyme first to give it a slightly better leaving group, to position it correctly, etc. So what we're going to do is, the first thing we need, we're going to do a nucleophilic acyl substitution reaction. Our nucleophile is ultimately going to be the sulfur of the cysteine on the enzyme. The leaving group is going to be coenzyme A. But to do that, to make it more efficient, we are going to turn this sulfur, which is a good nucleophile already, we're going to turn it into an awesome nucleophile by giving it a full negative charge. And we do that with a proton transfer. So a base nearby in the active site rips that hydrogen off, and the electrons snap back onto the sulfur, giving it that full negative charge. Okay, so now that sulfur is a great nucleophile, and it can swoop in and attack the carbonyl carbon of our coenzyme A. I'm sorry, of our fatty CoA. This carbon right here, that carbon has a slightly positive charge, so it's an electrophile, and the sulfur is going to be attracted to it, so it'll smack into that. The weakest bond, the pi bond, is going to break. The electrons will go up onto that oxygen. So that oxygen now has 3 lone pairs, and therefore a full negative charge. And the sulfur will be bonded to it. So now we have a tetrahedral intermediate for our nucleophilic acyl substitution. Now this oxygen up here has a full negative charge. It's very unstable, so it wants to come back down and reattach to the carbon down here. This carbon still has a slightly positive charge because it's bonded to electronegative elements that are stealing its electron density. But before it does that, we need to make sure that this coenzyme A is the leaving group. And so the enzyme does a proton transfer, and it positions it so that the sulfur here rips off that hydrogen, and the electrons snap back onto the base. So this base is now neutralized, and that hydrogen is going to be attached to this sulfur. And because that sulfur has 3 bonds, it's going to have a full positive charge. So that is great leaving group now, and so when this oxygen snaps back down, it kicks that leaving group off. So that leaving group then, that sulfur then takes those electrons, they neutralize the positive charge that was there, and that acts as a leaving group. Okay, so we have coenzyme A again. So this was really a catalyst. It ends exactly how it started, as coenzyme A. And this lone pair takes its negative charge and forms a pi bond to that carbon there. So again, that acyl group is being transferred like a sort of hot potato from one molecule to another. Once it's in the right enzyme pocket, the enzyme can position the correct molecule to react with it. That's why it's going into all these enzymes in the first place and not just doing one nucleophilic acyl substitution. So once our DGAT, or diacylglycerol acyl transferase enzyme, has this new acyl group on it, we can react it with our diacylglycerol. Now, and then we'll very excitingly be left with our triglyceride. So in this case, again, we have the nucleophile. It's going to be this oxygen. The leaving group is going to be the enzyme. And we're going to do a nucleophilic acyl substitution. Now, to make this nucleophile, this oxygen nucleophile, a better nucleophile, because right now it's a weak nucleophile, the base is going to rip the hydrogen off of it. The electrons will snap back onto the oxygen. So when that hydrogen leaves, it's bonded to that base now, which has a positive charge there. And the electrons snap back onto that oxygen. So that oxygen had 2 lone pairs, now it has 3 and a full negative charge. So now that oxygen with a full negative charge is a strong nucleophile. And because it's a strong nucleophile, it can attack our carbonyl carbon. So it can swoop in, attack that carbon, the weakest bond, the pi bond, will break. The electrons will go up onto the most electronegative place nearby, that's the oxygen. That oxygen now has 3 lone pairs and therefore a full negative charge. And this oxygen will form a bond to that fatty acid chain. Now, right now, this oxygen here is very unstable. It wants to snap back down to recreate the pi bond because this carbon is slightly positive, but there's no clear good leaving group. So we're going to do another proton transfer to turn this cysteine, and therefore the enzyme, into a good leaving group. The lone pair here attacks the hydrogen. Bond electrons snap back onto the base. That neutralizes the positive charge that was there. And now we have a bond between the sulfur and the hydrogen. Now sulfur has 3 bonds here and therefore it has a full positive charge. So it's not very stable. But that's why it's going to be such a great leaving group. Because when this swoops back down to recreate the pi bond, this really wants the electrons in this bond more than this oxygen wants electrons, and so this is going to be the leaving group. This bond is going to form electrons that stabilize what was the positive charge there. And so this whole thing is our leaving group, the DGAT enzyme. Meanwhile, this lone pair becomes a bond. And that gives that oxygen there a neutral charge. And what we are left with is a triglyceride. Now let me redraw this so that it doesn't look quite as funky. So there's going to be this bond between that carbonyl carbon and the oxygen there. And this carbonyl, I'm just going to reorient it. And that is our triglyceride. So we have resynthesized our triacylglycerol, or our triglyceride. So the point is, this is exactly how it started when you ate it, but now instead of being in your digestive tract, it is in your intestinal mucosa like this. And once it's like this, it is not going to be soluble in your blood. So your body will put it into a blob of other lipids. So you'll have a whole bunch of lipids like this in a blob, and around it you'll have phospholipids with their fatty acid tails that are nonpolar and their polar heads. And something like that might be called a chylomicron and things like that. And there might be proteins on here too, helping it to mix. Something like this could then travel through your bloodstream to your tissues, where this is going to get broken down to give you energy. But so far, your body has achieved getting this thing into your intestinal mucosa, and now it can transport it to your tissues. So you've resynthesized the